Hello everyone, and welcome back to the Edmund Optics Imaging Lab. I'm your host, Nick Sischka. In the last two labs, we started covering things like lens basics from focal length and working distance, and in the previous lab we covered a little bit more complex topics like how changing your sensor size can actually impact your overall system resolution even if your pixel size stays the same, and using optics to help to compensate for some of that. In this lab, we're going to talk all about two things, f-number and color, and how those two specific specifications can actually really impact your overall system level performance. Before we dive into some of those things, in case you're just joining us, a couple of notes for you. These demos are not being done live on the air right now. I did pre-record these. However, I did do these experiments real time, so if there's any minor mistakes or anything like that happens, please bear with me as I work through them. It's part of the fun of doing these for real. Secondly, the advantage of having me record these is that I can actually be online right now with you guys answering any questions that might come up, and I can answer those questions real time. So I also have a team of expert engineers standing by with me as well who can also help answer your questions, so please feel free. Any questions that come up, please drop them in the chat and we will be happy to help you. If you happen to catch this not live during the Imaging Innovation Summit, and you're seeing these after the fact, please feel free to reach out to our tech support. We'll be more than happy to help you guys answer any questions that you might have. So let's go ahead and dive into this lab here. As I mentioned, we're going to be talking about two things, f-number and color. So once you've gone through your specifications and you've decided this is the lens that I want and this is the camera that I want, and you make your choice and you thread it all together, the only two things that you can change in your system in order to impact your performance is the f-number and the color. You know that your working distance is already set because you ran your calculations and you know that you need to be so far away to get a specific field of view. And there's nothing else that you can change other than purchasing another lens besides these two things. So let's take a look at the setup that we have here. I have a Dalsa Genie Nano. This has the Sony IMX304 in it. It is a 1.1 inch sensor that has 3.45 micron pixels. I have an Edmund Optics 35mm HP series lens. This is from our 1.1 inch high performance line. And then I have three different targets that are back here, and these targets are USAF targets. I'll explain what that is in a minute here, and I have them stacked vertically here. And so there's 2 inches between each target, and so that means that we have a total of 4 inches here. The target that's in the center is in the center of the individual vertical grouping as well. And so this lens is currently focused on this target in the middle. And then what we have for illumination is an advanced illumination 8-inch side-fired backlight. It's giving us a really nice even illumination profile right now. So I'll go ahead and jump into what we're actually going to be doing here. And first we want to take a look at what happens when you start to change the f-number of a lens. So the f-number of a lens is the aperture size. And as you increase the f-number, your aperture is actually starting to go down. So if you look down the front of the lens and you start to increase that f-number, you'll see the aperture actually start to shrink. And that's letting in less light, and it's also increasing our depth of field. Let's take a look at how that depth of field changes as I increase my f-number. So right now, this lens is at f1.8. That's as fast as the lens can run. When I say fast, that's a typical term in optics. We sometimes talk about the speed of a lens. And if a lens is running faster, that means it's running at a lower f-number. If it's running slower, that means that it's running at a higher f-number. So right now, this lens is running, as said, as fast as I can at f1.8, and I'm focused on this central target here. And if we look at what this target is, it is, as I mentioned, it's a 1951 USAF target, United States Air Force target. And these targets have alternating patterns of orthogonal bars that decrease in size as the target spirals into the middle. And as we go up in what we call our group number, this would be a grouping here, as we jump from group 0 to group 1, for example, and we look at the specific element, say we're looking at element 2, the frequency actually doubles going up in group number by 1. So that would mean our feature size gets divided in half there. And we're looking at these targets, and we can clearly see that at f1.8, the middle target here is in view, but the other two targets are clearly blurry, right? We cannot see them. So let's see what happens as we increase our f-number. And I have this camera set to auto exposure, so it's going to be compensating for the light loss as I adjust the aperture. So you'll see some darkening here as it's going through its adjustment. but I'm going to slowly increase. And what we'll see here is that the writing specifically, the Edmond Optics writing here on these two targets, is coming into view as I'm increasing my F number. And this makes sense. Our F number is increasing. That means that our depth of field is increasing. And this lens has a maximum F number of f16, which is right here. And we can see now that we have as large of a depth of field as we can. And we can definitely make out the Edmond Optics here. And we can still have what appears to be relatively good resolution. So I'm going to open this back up. And it's generally understood that that's about how F number works. But one thing that's less understood about F number is how that actually impacts the overall performance of the imaging system. And what I'm going to do to pick on that is I'm actually going to swap out this central target here with one of the star target arrays that we're used to seeing from the other labs here. So let me just swap this in. I'm going to leave the other two targets so that we can come back and take a look at them. But I really want to focus on what's going on with this central star here. So I'm going to zoom in. I just want to make sure that I have as good a focus as I can here. So let me just double check to make sure I didn't bump anything. So we're good about here. So there's a couple things I want you to first notice. And the first thing is that we have relatively low contrast out here. We still have a good image, but the contrast doesn't look as high as it potentially could be. I think we might be able to squeeze some more contrast out of this. And then down here we have a relatively small blur circle, but let's see what we can do to improve this by changing our F number. So I'm going to start by going from f1.8 to f2.8. And the first thing that you'll notice is the low frequency points here really darkened up. Our contrast really increased. Our blur circle maybe got a little bit smaller, but the more profound impact was actually up here where our contrast increased at our low frequencies. And the reason why that happened is actually because as we've increased our F number, we reduced what we call spherical aberration. Spherical aberration from an optics point of view is the change in focal length with respect to pupil position, but that doesn't really mean much to us non-optics nerds. And what it functionally means is that as you have a large aperture, you're getting a wide range over which all kinds of light rays are focusing. And as you decrease that aperture size, or as you increase your F number, you're actually narrowing that window over which light rays are focusing. And so we're losing some of that blur, which is being collected onto the image sensor. And that's why these low frequency points here darken up. So let me just back up to f1.8 and we'll see how the contrast is. And then again, it goes much more gray and our contrast lowers, but as we increase that to f2.8, we see our contrast come back to normal. This lens was actually designed at f2.8 and that's where it's going to have a very good balance of throughput as well as resolution. Now I want to talk more about resolution, because we saw obviously an increase in resolution as we went up in F number here. But what's going to happen is we keep increasing our F number. So as I go to f5.6, we actually start to notice performance start to break down and start to get worse. And I'll go ahead and skip directly to the punchline because this is the fun part. As I increase to f16, notice what happened to the size of our blur circle here. It really got larger. And that's because at this point, yes, we have a very small amount of spherical aberration because our aperture is so small. But the other thing that has happened is that diffraction has taken over the performance of this lens. We've hit what we call in optics our diffraction limit. And essentially what happens is that once you reach your diffraction limit, as you continue to increase your F number, your performance is actually going to get worse and worse as you continue to do so. So I can actually increase the F number just a little bit more on this lens to get a really dramatic idea of just how much diffraction can impact the overall performance that we can have on the lens. So if we zoom out here from our central star, we can see that we have a very good depth of field, and we can make out this Edmond Optics very well, but you can even see on our stars that we have relatively low resolution here. And this is something that's really impactful, especially as pixels continue to get smaller, and that is that your F number is going to play a huge role in what level of performance you're able to achieve. And a good rule of thumb that I like to use, this is a good one to write down, is that in general, if you're trying to maximize the performance of your camera, you never want to run your lens at a higher f number than twice your pixel size. So as a quick example, using this Dalsogini Nano camera here, we have a 3.45 micron pixel in this camera. This lens is designed to hit that pixel size, but it's only designed to do so at a reasonable f number. So the maximum f number that you would expect to be able to use this lens at, while still being what we call pixel limited from a system point of view, is f6.9. And once you go beyond that, you're no longer taking advantage of the small pixels and you're no longer able to resolve down to that particular feature size. So that can have a huge impact in what you're actually trying to view. In this particular case, if you're just trying to look at something that's, say, the size of this EO here, you would be just fine running at f16, especially if you need to see it over a large range. The important takeaway here is that you cannot continue to increase your f number just to buy more depth of field, because you will very quickly start to lose resolution performance. So speaking of resolution and performance and f number, I want to actually hand this over to Teledyne Dalsa to talk a little bit about cameras.
Hi everyone, my name is Filip Szymański and I'm here on behalf of Teledyne Imaging. Today I'm going to be talking about the importance of signal-to-noise ratio, or SNR. So you might be wondering, why is it important to consider SNR? Well, it's the measurement of how much light an imaging system can capture, convert into a digital signal, and its relationship to how much noise is generated through that process. So by having a lower noise level, you can have a higher SNR and a higher overall clarity to your images. The things that can affect this include not having enough light, increasing gain, lens characteristics such as having too small of an aperture, or not having the right light source, whether it be LED or tungsten, or sensor quality. And when looking at how you improve SNR, it's important to consider those sensor characteristics, such as having good QE curves, larger pixels so that each individual pixel is actually able to capture more light, having a higher full well capacity, or even looking into different types of sensor technology, such as back illuminated sensors, which have a higher sensitivity to traditional designs. So that's a lot to consider. There's a lot of factors in making these types of decisions. So Teledyne Imaging has a diverse portfolio, and our imaging experts are happy to help you find the best solution to your particular application. Feel free to contact us at luminera.info@teledyne.com.
Awesome, thank you so much for that information on cameras. Now, while Teledyne was talking, I actually went ahead and switched around some stuff on our setup here. I removed our two other USAF targets, and I just left the star target here. I changed out our camera to an IDS camera that has, it's one of their CP cameras. This has an IMX from 264 in it from Sony. This has the 2/3 inch sensor and the 3.45 micron pixels. And then I also changed our light to a Metaphase Technologies RGB backlight. So this backlight is going to allow us to change colors, go from red to green to blue, because that's what we're going to be looking at in this portion of the lab. But before I go into that, I do want to hand this over to Metaphase and let them talk about how choosing your illumination wavelength can make a huge impact on your overall performance.
Hi, this is Mark Colvitis with Metaphase LED Lighting Technologies. Metaphase is a company that's been designing and fabricating LED illumination controls for about 25 years for machine vision, microscopy, military, scientific, motion analysis, and cinematography type applications. We're a long-term supplier and a customer to Edmund Optics. Edmund has been kind enough to ask us to do a quick presentation on some items to consider when determining the best LED wavelength when designing a typical imaging system. One of the other presentations will cover how to select the best type of LED illumination, but this presentation is about selecting the proper wavelength. I'm currently the technical sales manager here at Metaphase, but was a former application engineer. This quick presentation is to cover some of the things I've learned over the years from suppliers such as Edmund Optics, and also things I've learned the hard way during some application designs and installations. Light is a small part of the electromagnetic spectrum and exists in tiny energy packets called photons. Different colors have different wavelengths and are expressed in units of nanometers or microns, the length of the wavelength. An object has the color of the wavelength it actually reflects. A material that reflects all wavelengths of visible light appear white. A material that absorbs all wavelengths of visible light appear dark. A color object absorbs the complementary color. Therefore, red would absorb green. A typical automated imaging system consists of image acquisition, which would be the camera, feature segmentation, feature extraction, decision making, and finally some output such as a reject signal for a reject mechanism. The initial step, and maybe the most important, is the illumination of the parts for image acquisition. Some will say that that's about 9/10 of the battle, is getting good image quality on the front end. It's important to have a repeatable, high contrast image in order to have a robust imaging system that minimizes the amounts of time the user has to go in and change parameters for their normal product and process variation. Some considerations are garbage in, garbage out. Poor image quality will result in low image performance. The goal should be to have a high contrast image where the features of interest in the image are displayed or stored for further processing and everything else is black. Remember that the lensing and its angular field of view will have effect on the uniformity of the captured image. A wide angle lens could result in a non-uniform image, even though the light source is very uniform. Safety. Keep in mind that some wavelengths require some eye and skin protection, such as UV. So here we're showing how you can use different color or wavelength light sources to highlight the colors of interest. In the upper left-hand corner, we have some color markers. And below that, we have the monochrome image when illuminating with the light source. Now, if we wanted to count or segment the blue markers from the background, we would use a blue light source or a 470 nanometer. And the same would be for the green. We could switch to a green light source, which would highlight the green markers in the scene of 535 nanometer, and finally the red or 660 nanometer light would be used to highlight the red markers. Metaphase makes monochrome, but also makes multispectral light sources where there's an RGB in the same light source, so you can do some color mixing or just have a single light source to extract the different color markers. In addition to the color of the object itself, you also need to keep the sensitivity of the camera itself in mind, such as this camera here is a typical CCD type sensor where it's very low in the 300ths or UV, and very low in the infrared, but peaks in the red. If you need to do something in shortwave, then you need to have a shortwave sensitive camera, typically in the range of 1000 to 1700 nanometer. Keep in mind that for most UV type applications, we're talking about something that fluoresces, where you expose it to ultraviolet light, but it transmits or fluoresces a wavelength that's in the visible spectrum. So a common mistake is that you need an ultraviolet sensitive camera to do UV applications, but if it's a fluorescing application, then you typically can just use a normal CCD sensor to do that application. Here we're showing a piece of FlexFix aluminum tape where the writing is, the print is red on the tape, and we're showing it with different wavelengths of lights. You can see we're using the green light, which is the complementary color to red. The text shows up as dark. When we use a red light, it shows up very bright. And when we use polarized light, you can see the printing itself removed and we just see the background. So this is a UV application where the manufacturer of the ice cream wanted a 2D barcode not only on the bottom of the package, but also on the front, but didn't want it visible to the consumer. So they used a UV sensitive ink and printed the 2D barcode, which fluoresced or turned green when exposed to a 365 nanometer light. So a bandpass filter was put onto the camera, so the only thing that would be observed and stored for further processing would be the 2D barcode. In conclusion of some of the considerations presented, You again want to choose a wavelength which maximizes the contrast between the object of interest and the background. Like the movie producers who used to yell light, camera, action in that order, you don't want to minimize the importance of having a properly illuminated image. You also want to consider the camera's spectral sensitivity when choosing a proper wavelength. And finally, remember that some wavelengths, such as ultraviolet, will require special safety precautions such as shrouding. Thank you, and I hope you enjoyed this presentation.
All right, thank you so much. That was some awesome information, Marcio, on the lighting side of things. There's so much to consider with lighting, and I've mentioned this before. It's very, very difficult in machine vision to make sure you get the lighting right. And if you don't get it right, it can make a huge impact negatively on your performance. So let's go ahead and dive into how color can actually impact that. Let's dig into some of the details that Marcio was talking about in terms of your interaction with your object, as well as the interaction with the lens itself. And that's what I want to focus on here, is less about the object, more about the lens. My object here tends to be relatively agnostic to the type of light that's coming through it. It doesn't really care what illumination I'm passing around it, as long as it makes it through the glass. And so in this particular case, I'm going to be using red and green and blue, and the individual object is going to interact with the light roughly the same way. Our lens, however, is not going to react the same way at all. And so I have here this 35mm lens, and I've focused it onto this star target, and it is currently at f16. So I purposefully increased our f number to really, really high so that we have this large blur circle. I'm going to zoom in really far here so that we can take a look at exactly what's going on. And what I'm going to do is I'm going to place my mouse cursor right here at this edge, and then I'm going to change the color of light that we're using. So right now I'm using red, and oftentimes red is talked about as being the most common machine vision wavelength. It's a question I like to ask when I do this in front of live audiences, which is, what color is your go-to color for illumination? And for the first few years of my career, it was almost solid 100% red. And I'm actually really happy to see now that other people are starting to talk about other colors in there. But traditionally, red is used in machine vision because it was an inexpensive choice to use monochromatic illumination. And they were inexpensive LEDs when they first started coming out. But let's take a look at how the different colors actually impact our lens resolution. So if I go from red here to blue, which is on the other side of the visible spectrum, let's take a look at what happens to our resolution. Look at the size of this blur circle and how much it got smaller. I know I just moved my mouse cursor from where it was, but I'll put it back here at where the limiting resolution is with blue, and I'm going to jump back to red. We see how much resolution we lost going from red to blue. And I'll set it back here. I'll do this one more time so that you can watch this. We can see a huge change in the resolution that we were able to achieve. It doesn't look like much. It's a small amount from an absolute sense, but we gained about 20% resolution just by changing the wavelength of illumination that we're using on this lens. And this has entirely to do with diffraction. There's an equation that we use that dictates diffraction limited resolution, and that equation basically states that the overall resolution that you can achieve is proportional to your wavelength and to your wavelength of light. So that means that as your wavelength of light actually starts to go down, the minimum resolvable feature size that you can have also goes down. So I guess I should say that resolution is inversely proportional to that. We're talking about a feature size. The feature size is going to go down as wavelength goes down. The feature size is going to go down as f number goes down as well. And we saw that from the first half of this lab when we were looking at increasing our f number, and we saw that the larger f number made the smallest object that we could look at much larger. So we have red and we have blue. And then the last color, of course, that we can take a look at here is green. And as we kind of expect, green is in between red and blue, and so the green performance lands right in between red and blue as well. And so blue definitely is going to have the highest performance. Red is going to have the lowest performance. Another question that comes up sometimes when I'm doing these live is, well, if we can just keep going to lower and lower wavelengths, why don't we? Why don't we use, what if I really want to get a suntan while I'm doing my machine vision experiment and I want to run this in UV, just keep going lower and lower? Well, issues with UV aside, from an optics perspective, you actually wind up having the glasses start to behave really interestingly down there. And when I say interestingly, I mean poorly. They start to transmit a lot worse, and they start to go haywire on their dispersions. And so it can be really difficult to maintain the optical design. And so even though theoretically you could achieve higher resolution with the lower wavelength there, most machine vision lenses aren't going to do well once you get below around 470 nanometers. Even when you get down into that violet 405, there are some lenses that don't start to perform actually relatively poorly. So usually in machine vision applications, I'll recommend to people to use blue or green. That also corresponds with, especially the green, with high quantum efficiency from the sensor side of things. And speaking of sensors, I actually want to hand this off to Kevin at IDS to talk about some fun things with sensors and with cameras and how pixel size can also impact some of what we're looking at here. Kevin, take it away.
Hey everybody, my name is Kevin McCabe. I'm a senior application engineer at IDS Imaging, and I'm here to talk about pixel size and why it matters in your measurement system. So, what's pixel size? Well, it's the size of a pixel in an image sensor. A bit of a circular definition, but it really is that straightforward. The pixel size not only includes just the sensitive portion of the pixel, it also includes the supporting electronics around it. But because of technology like microlens arrays, we can fudge it and say that the pixel size is the size of the sensitive area for our purposes here. The pixel size in a measurement system actually really defines the resolution of it. So let's take a really easy example. Let's say we have a sensor with really tiny 1 micron pixels. And we pair with it a lens with a 1-to-1 magnification, and that lens then projects those pixels out into your measurement field of view as the same size as they were. So 1 micron pixels in the scene as well. So that means you have a 1 micron capability in that system, right? Sort of, but not really. Right? When you're doing measurement, you're really looking for contrast. You're looking for things like edges, which require contrast. So a better rule of thumb is at least 2 pixels to see a feature, or really 3 pixels to truly see a feature in a scene. Why not always go with small pixels? Well, they have quite a bit of disadvantage as well. They give you high resolution in a small area. They're usually cheaper because they take less space on a semiconductor wafer, and sometimes it's easier to get more depth of field with them, but they aren't the best. Again, contrast is king here with measurement systems. You have to think of it that way rather than just in terms of a distance. What you have when you move to larger pixels, you tend to get better signal-to-noise ratio. There's better dynamic range as well. The signal-to-noise ratio is better because you're capturing more signal with a larger pixel. More photons can be converted into electrons because of that larger physical size of the pixel. The better dynamic range comes from usually a larger area pixel has a deeper pixel well, which can capture each pixel with a particular exposure, can capture a different amount of light in the same scene without getting saturated or losing data. Large pixels are actually easier to lens as well. Really tiny pixels, it's really hard for lenses to resolve down to the size of a small pixel like 1 micron. That is pretty dang small. In reality, most like high resolution small sensors, you don't get the true resolution because the lens itself doesn't resolve down. I'll let the lens experts talk on that a bit more, but that's one of the big factors. And you can still have high resolution sensors with larger pixel sizes. For example, you could have a 5 megapixel sensor that's 2/3 inch with something like 3.5 pixel size quite easily. And that's kind of a sweet spot. So hopefully I was informative here, and enjoy the rest of your day.
Thanks so much, Kevin. That was awesome. So that's all I have for you guys today for this lab. Just a really quick summary. Our F number and our wavelength of light that we're putting into the lens, those are the only two variables that we can change once we've actually selected a lens and threaded it onto a camera. And they both have very profound impacts on the overall system level performance that we can achieve with a lens. Thanks so much for watching, guys. I'll see you in the next lab.